All right, good morning. So, let's start with 4B here at the top of more PTVn tables. No typos in this sheet. Sorry about that typo. I was going really fast when I was making that. Yeah, those were crazy. But jumping in here to 4B, we can see that we have volume, temperature, and pressure all present in my problem. The only thing that's being held constant is n, so I can cross out the n column, but I need to use the other three. And I can see that it's really straightforward about what my initial and what my final is. It just tells me straight up 150 cubic centimeters, 273 Kelvin, and 101 kilopascals. And we're changing those conditions to 400 K, so that's your temperature, 50 kPa, and we want to know what the new volume is, so I'm going to put my question mark right there. All right, so I hope you figured out by now, because the last question on the first sheet had multiple things changing. The way that we do this is, instead of multiplying our initial condition, in this case 150 cubic centimeters, instead of multiplying it by just one ratio, we're just going to multiply it by two ratios. So I'm going to take that, well, first I need to do my effect row, right? I see that my pressure is going down. So I think, okay, when pressure goes down, what effect does that have on volume? Because remember, I'm solving for volume. Okay, so I'm going to say, what effect does that have on volume? And I'm going to think about it. P down, that must be V up, right? Because remember, those are the ones that are opposite. And I see that my temperature is going up. And when temperature goes up, volume goes up as well, right? Remember, that was the last one in your summarizing gas relationships notes, that temperature in Kelvin is proportional to volume. All right, and then we know that since volume is increasing for both of these, I know that my volume is going to go up. So it's going to be bigger than 150. So I'm going to take my 150. I'm going to multiply it not by one ratio, but by two ratios. And I just need to decide which number goes on top for each ratio. The first one I'm going to do is I'm going to do a ratio of pressures. And it doesn't matter what order you go in, but I'm just going to do them in order as they appear in my table. Ratio of pressures first. So since I want my pressure to make my volume get bigger, I'm going to put the bigger number on top. I'm going to put the 101 kPa on top of the 50 kPa, because that is a ratio that is bigger than 1, right? If I punched just this into my calculator, I would get some number that's bigger than 1, and multiplying a number that's bigger than 1 by 150 will give me a number that's bigger than 150, and that's what I want. I want something bigger than 150, so that's why I'm putting that 101 on top. That's just a review from yesterday. This is where it's different, because now I have a second relationship or second ratio to keep in mind. I also need to account for this temperature change. My temperature is increasing, which makes my volume increase. So my temperature ratio, right, this ratio right here, should also contribute to making my volume bigger. So I'm also going to put my larger one on top here. Cool. So I just want you to notice something really quick. For my ratio of pressures, my initial went on top, right? But for my ratio of temperatures, my final went on top. So there is no rule, or you should not even like be thinking about like trying to make the initial always go on top or trying to make the final always go on top. What matters is what we decide in this effect row down here. That's what matters. That's how we decide which one's going to go on top. What effect do we want it to have on the thing that we're solving for, right? And if it's going to make it go up, then I don't care if it's the initial or the final. Put the bigger number on top, right? Put that 101 on top. Put that 400 on top. And now we can run our calculation and we'll get the right answer. I don't have my calculator ready. Sorry, hold on. 150 times 101, divide by 50, times 400, divide by 273. I get 444. And to check my unit, that's going to be cubic centimeters. And there's my answer. All right. I'd like you to try question 5A, and then I'll be checking in with you in a second. All right. But try it first, and then like pause the video, give it a shot, and then once you think you know the answer, you can play the video. All right, here we go. So this time we know that the tire contains 15 units of air particles. Since we're talking about particles, right, units of air particles, that's going to be amount. So I'm going to say 15 U, and it has a volume of 160. So I'll put that right there. Under these conditions, the pressure reads 13 psi. Then the tire develops a leak. When the tire develops a leak, we know that some air is going to leave the tire, right? And now it contains 10 units. And it has contracted, right? The volume is decreased down to 150 milliliters. We want to know what would the pressure be now. All right. So this one's gonna be a little different because there's something interesting going on here. We have to decide what effect my volume change and my amount change, what effect do these changes have on pressure? So we'll do that in our effect row. I can see that volume is it going up or down? It's going down. And I know that when volume decreases, remember that we are restricting the amount of space that those particles have to move around in. So when volume decreases, that makes pressure go up. But on the other hand, I also can see that the amount of gas in the tire is going down. And what effect does that have on pressure? Well, if there's less particles to bounce around in the container, of course, there's going to be less collision, so that's going to make the pressure go down. So hold up. We have one of our variables, volume, contributing to a pressure increase, and we have another variable, amount of gas, contributing to a pressure decrease. How are we going to deal with this? This doesn't make sense. Well, it turns out that we do the math actually the exact same way that we did it before. It is okay for our two variables to disagree because one of them is going to outweigh the other, if that makes sense. What really... Yeah, so when we do our math, right, like right now, we don't know what the effect is because maybe, I don't know, maybe the volume increase, or sorry, the volume decrease and the amount decrease are going to like offset each other and there'll be no change in pressure. I don't know. We don't know. Or maybe the volume has a bigger effect or maybe the amount has a bigger effect. In order to figure it out, we have to do the math. So, and here's how we do the math. I'll take my 13 psi. Again, multiply it by 2 ratios since I am changing two things. And I'll just take it one ratio at a time. I'll look at my volume here. I can see that my volume is going down, which makes my pressure go up. So if this is my volume ratio, I want my volume ratio to contribute to making this 13 a bigger number. So then I'm going to put the bigger number on top. Whoa. So then I'm going to put the bigger number on top, 160 ml over 150 ml, right? Because that is the effect that volume has on this tire, right? The volume is getting smaller, and that does make the pressure increase. It does. We've seen it. All right, and then for my second ratio here, this is going to be a ratio of amounts. We have 15 units down to 10 units. That is definitely a decrease, and that definitely does make my pressure get smaller. So let's set up my ratio to reflect that. I'll put this time, my smaller number on top. 10 units over 15 units. See? And that's okay. So now I can run my calculations, and it works just fine. 13 times... Before you do the calculation, can you just like think about it like in common sense? What's going to happen to the pressure? I mean, we got a leak in our tire, yeah? Okay, divide by 150 times 10, divide by 15. Got 9.2. 9.2 psi. All right, so for the rest of them, keep going. The only thing I'm going to say is watch out for Celsius if you have a Celsius temperature, you have to convert it to Kelvin, or remember, otherwise it's not directly proportional. We said that our graph for Celsius versus pressure and our graph for Kelvin versus pressure, we want to use the one that allows us to do this direct proportionality math. Unless you want to jump in there and do some y-intercept stuff, I don't. If you want to do it, if you want to figure out how to make that happen, then I guess you can use Celsius. But if you don't want to do all that mess, just convert to Kelvin. And the way we do that, remember, is we just add 273. So it's not even a difficult calculation. All right, so good luck with that. I might try to get answers for you up later in the morning, but I don't know, no promises. Remember, you have that mini quiz that is happening in the last 20 minutes. The sub will tell you when it's time for you to set up your privacy folders and put all your notes away. He knows that it's a closed note test, all right? And it's on Chromebook, so be ready for that. Alrighty, I will, again, see you on Monday. Thanks for working hard today and locking in. I know that since it's like homecoming, exciting times, that maybe you'll be a little bit antsy, but just do your best. Stay locked in. We got lots to do, and I'll see you when I get back.